All right. So now we have seen that we have expressed, what we have done is not exactly quantize the original formula for the diffeomorphism constraint, but multiply this diffeomorphism constraint by a triad, contract the diffeomorphism constraint by a triad. So we got a modified equivalent diffeomorphism constraint, and now we find we can express this modified diffeomorphism constraint in a expression which is very similar to Hamiltonian constraint. Yeah, the only difference is that we insert a Lie algebra generator in the trace. Okay, so therefore we can, this expression can be quantized similar to the Euclidean Hamiltonian constraint. Quantized similar to C0. All right. Well, again, and this trick is again invented by Thomas Tiemann, I think, in 2007, maybe 2000. I don't remember exact year, so either 2007 or 2004. Okay. All right. So again, we apply the formula. So again, we are actually not quantizing the Cj, but Cj multiplies the sign determinant of E. So similar, because the quantization is similar to the Euclidean term. So again, we are going to use EA, EB. Q equals times C. Okay. All right. So now this sign E Cj equals to 16 theta squared and epsilon ABC. Okay, so maybe I give you a reference about this treatment of diffeomorphism constraint. So you can find, so this is more precisely is not only Thomas Tiemann, but by Christina Giesel. And Thomas Tiemann in, I think this paper is called AQG. So algebraic, I mean, the title of the paper is called Algebraic Quantum Gravity. So it is in 2000, I think it's in 2006 or 2007. I don't remember exactly year. I think it should be 2006. Yeah. So AQG 1. Yeah. So it has 3 papers and with the title AQG, but this is located in the first paper. Okay. Yeah. All right. So secondly, so we are going to discrete again using the discretization trick for the similar to the Euclidean Hamiltonian constraint. Namely, firstly, we are going to replace this curvature by using loop holonomy, the holonomy around the minimal loop, around the minimal plaquette. And secondly, we are going to use holonomy to replace this A in the Poisson bracket. So we are going to using discretization ij. So alpha ij is the minimal loop. So this is equals to 1 plus integral xij xi dxj fij. Yeah, there's no sum in ij, no sum. No sum. Well, and this partial Sij, the boundary of Sij is alpha ij. Sij is a square bracket plus order 3. So these formula are holds. This formula holds only at the continuity, and similarly for this. Equals minus 1. Up to higher order in mu. So the leading this formula leading order is of first order in mu, because this is integrated along ER. And the above formula for the curvature, the leading order of mu square, because this is a surface integral. Okay, so now again we use this discretization. Well, the same trick before. We integrate this expression in one of the cube, okay, and then average over 8 cubes around the vertex at the vertex. Okay, so, and then divide by 1/8. So here we divide by 1/8. So replace this numerical factor 16 by 2. Okay, and in this formula you get a minus sign. So therefore in front there's a minus sign. And now we have. Okay. Now what we do is making average over 8 cubes at the vertex. Okay, and the result is CJV. So this is a discrete expression of CJX. So here X becomes the vertex of the lattice. I promised that there's you replace this 16 by 2, 16 by minus 2. S1, S2, S3 equals to plus minus 1, and sum over I1, I2, I3 from 1 to 3. And here S1, S2, S3 in epsilon I1, I2, I3. Okay, and now trace tau j H1, S1, 2, S2. Okay, so this is the loop polynomial to discretize the curvature. Then we have HHB term. 3, 3. So you can see that the formula is very much similar to the Euclidean Hamiltonian constraint. The only difference is that you just insert the algebra generator. All right. So now the quantization is again straightforward. You replace everything by operator. You replace the Poisson bracket by commutator. Quantum version of the diffeomorphism constraint is minus HR square beta 2 epsilon I1 S3. Okay. trace. Okay. Okay, this trace is always respect to 2 by 2 matrices because the holonomy operator is operator valued 2 by 2 matrix. Now you place Poisson bracket by commutator. Okay, so now you get the operator expression for the diffeomorphism constraint. Again, this expression was similar, very much similar to the Hamiltonian constraint. Well, this is well, again, the difference, there's a difference between this expression and the Hamiltonian constraint is that this is not exactly gauge invariant, but this is actually gauge covariant. Yeah. This is because you see you have an index j, and this j is a gauge index, right? The reason is that we express this this diffeomorphism constraint by the earlier diffeomorphism constraint by EAJ, and this J is a gauge index. It's transformed in SO3. So at most you can imagine this operator is not gauge invariant but gauge covariant. DJ hat V is gauge covariant. It's gauge covariant. So it means that under the gauge transformation, it transforms Cj V transforms to a certain matrix lambda jk. CKV lambda jk. Probably like this. Yeah. And this lambda belongs to SO3. Yeah. So this J is like the vector index of SO3 of the rotation. So this lambda has to be SO3 matrix or the in one representation of SU2. Okay, so it means that this operator is not going to be defined on the gauge invariant wave functions because it will transform. It is not exactly gauge invariant, so it acts on the gauge invariant wave functions. The result is not necessarily gauge invariant, but rather gauge covariant. But at least what you can so what is useful is that, for example, so later on you will see this operator will be always present in squares. So for example, this quantity, it is definitely gauge invariant. Over j from 1 to 3, and it turns out that this quantity it is the quantity we are actually using later on. So so in the end, we always use this operator to construct some operators which are indeed gauge invariant, although this diffeomorphism constraint itself it is not. All right, so I think I better stop here, and because next yeah, it's good time to stop because next time I'm going to talk about a little bit different topic, although still related to the constraint, but another aspects. Yeah, so at least from these lectures we are able to quantize all the constraints. So this finished the section about quantizing constraints, and there are 3 kinds of constraints: Gauss constraint, Hamiltonian constraint, and diffeomorphism constraint. And now we are able to quantize all of them on the cubic lattice defined on our Hilbert space. Okay, and here the Gauss constraint, the result of Gauss constraint is just the gauge invariant wave functions, and we have the Hamiltonian constraint. Although we haven't able to solve the constraint equations, at least we are able to write those constraints as operators on wave functions of diffeomorphism constraints, on the wave functions of gauge invariant Hilbert spaces. Okay, and furthermore, we are able to write down the diffeomorphism constraint, but this diffeomorphism constraint is not exactly gauge invariant, but it is gauge covariant. It means it cannot be defined on the Hilbert space of gauge invariant wave functions, but it can be defined on the earlier Hilbert space, which is general wave functions, non-gauge invariant wave functions. More precisely, it can be defined over there. But in the end, later on, as you will see, when we use this diffeomorphism constraint, it will be always present in square. So in the end, it will be gauge invariant. Okay, I think that's all for today. So if you have any questions, you should ask. Okay, so if there's no question, so we should stop and see you next time.
Thank you.